Hey everyone, welcome to Lecture 3 of the Quantum Student Society. Today we're going to be discussing quantum states and superposition. So we're going to be talking about superposition, specifically classical and quantum superposition and the Schrodinger's cat experiment. And we're also going to be discussing creating superposition, specifically the beam splitter. So what's classical superposition? It's when you add two physical quantities and to make a new physical quantity, which is completely different from the original two quantities. So take noise-canceling headphones, for example. They use superposition by creating sound waves with the same magnitude as the incoming sound wave, but completely out of phase, so it cancels the original incoming sound wave. And another common application of classical superposition is finding the total magnitude and direction of quantities such as force, electric fields, magnetic fields, and other stuff. And now what's quantum superposition? Quantum superposition means existing in multiple states at the same time. So take a coin for an example. If you flip a coin, its definite state has either two possibilities, right? Heads or tails. But when we're talking about quantum superposition, we'll say that the coin is heads and tails at the same time. And to look further into this, let's dive into the Schrodinger's cat experiment. Suppose you have a cat in a closed box with a single atom that has some probability of emitting deadly radiation at any time, right? So the cat can die. And since radionuclear decay is a spontaneous process, it is impossible to predict for certain when the nucleus decays. Therefore, you do not know whether the cat is alive or dead unless you open and look into the box. So it can be said that the cat is alive and dead at the same time, with the same non-zero probability, which means that the cat is in a quantum superposition state until you open the box and measure its actual state. And upon measurement, obviously when you open the box, you'll know the cat is alive or dead. But the point is that when the box is closed, the cat is dead and alive at the same time. But when you open the box, the quantum superposition collapses and it enters a non-superposition state. And now let's watch a brief video just grasping this concept further.
Hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrodinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant freaking hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they react to various forces. But then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. Think to say, what now? My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand it. Say you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me here. Now say that there's a 50-50 chance that one of the radioatoms is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of funding the sciences. So there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead, and an equally good chance that the vial hasn't been broken and the cat's just kicking it wondering what's for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time, because that's how quantum objects act. So then that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws, so it, just like every other cat in history, is either alive or dead. Schrödinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom has decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrodinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrodinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. And alternatively, the point is that the universe is pretty frickin' weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive, and one in which the cat is dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below and I'll, do my best. Also, if you have an idea for I don't think that means what you think it means, please let us know about that too.
Now let's look at creating superposition with a beam splitter. So we see partial reflections in our everyday life. So for example, if you look at your window at night, right, and you turn your lights on in your room, you'll see both yourself and what's outside. So this is called partial reflections, where some light transmits through and some light reflects back. Other examples are two-way or one-way mirrors, sunglasses reflecting some light, or the water surface showing both the sky and you can see under the water. And a key insight is light can be partially transmitted and partially reflected. So what's this beam splitter device? Well, it's a glass or crystal surface with special coating, which splits incoming light into two different paths. And it's typically like a 50-50 split, but depending on the angle, it can be customized. So this is the glass, this is the original light beam, and it's being split off into two. One's being reflected and one's going through. And some common types of beam splitters is a Q beam splitter, which is two prisms glued together. Another one's a plate beam splitter, it's a thin coated glass. And another one's a pellicle beam splitter, which is an ultra thin membrane. So what's this classical behavior? So with a laser beam, it emits many photons, right? So it inputs 1,000 photons per second, and photon is a measurement of light, and it splits it into 50-50. 50-50 light one goes through for 500 photons per second, and the other reflects back 500 photons per second. And the energy conservation for this is, the input power must equal the output powers, right? You got to add them together, because conservation of energy, that's the law. That energy can neither be created nor destroyed. And each output beam is dimmer than the input, obviously, because you're splitting the photons. So a classical analogy is like cars at an intersection where exactly half turn left and half go straight. So the single photon question, we ask, if we send one photon at a beam splitter, you would expect it either goes to path A or path B, and there's a 50% probability for each path, which is like flipping a coin. But how do we test what really happens? Well, the quantum reality is that the photon takes both paths simultaneously. That's what quantum superposition is. It exists in both paths at the same time. So the input photon is square root of 2 transmitted, and the other one's reflected. So what this means, not 50% of photon in each path and not uncertainty about which path. The whole photon is in superposition of both states at the same time, and it exists in both paths until measured. So you don't know until you measure it, similar to the Schrodinger's cat experiment. Let's look at an example for the beam splitter. It's called the Mach-Zehnder interferometer.
This is the Mach-Zehnder interferometer, what has been explained by Benjamin Schumacher in his TTC course of The Physics of the Microscopic World. In this interferometer, a light beam from a laser source is passing through a beam splitter. The beam splitter is a half-silvered mirror. which reflects 50% of light and transmits another 50% of light. It splits the light into two beams. The upper beam is reflected and the lower beam is transmitted. Both beams reach full silvered mirror fixed at two corners to reflect into another beam splitter, which is a half silvered mirror. There are two light detectors labeled A and B at both exits. As the lower beam is negative in amplitude and interferes with upper beam, the light beam always strikes detector A. No light beam strikes detector B. Let us see how this experiment goes in our lab. This is the laser light source producing red light with 650 nanometer wavelengths. This is the aperture to reduce the light intensity. This is the beam splitter of half silvered mirror, which reflects and transmits 50-50 lights. These full silvered mirrors, which are fixed at both corners, reflect the light with a phase shift of 1 pi. Finally, both light beams reach the second beam splitter of half silvered mirror, which reflects and transmits 50-50 lights. The combined light beam is expected to strike the detector A. When I set it up and turn on the laser light, the light beams reach both detectors. These are not combined and don't strike only detector A. I am able to see the lights strike both screens. I tried with perfect alignment of beam splitter, mirrors, rotating beam splitters and all possible ways. Still, light beams reach both screens and the result is not as expected. I googled it and found the reason for this behavior. The phase shift of light beam needs to be considered in order to understand this behavior. Dielectric beam splitter is the one we need to do the test which shows expected result. The light beam reflected by the front surface of dielectric beam splitter doesn't occur phase shift, but the light beam reflected by the back surface does occur phase shift. First, let us follow the upper light beam until it enters into the second beam splitter. In the beginning, it is transmitted by the first beam splitter and occurs no phase shift. Then it is reflected by the right full silvered mirror and occur phase shift of pi. Now the upper beam has phase shift of 1 pi. Next, let us follow the lower light beam until it enters into the second beam splitter. In the beginning, it is reflected by the first beam splitter and occurs no phase shift. The light beam reflected by the front surface of dielectric beam splitter doesn't occur phase shift. Then it is reflected one more time by the left full silvered mirror and occur phase shift of pi. Both beams are having phase shift of pi. If we follow the upper beam inside the second beam splitter, the upper beam is splitted by 50% reflected and 50% transmitted. The light beam reflected by the back surface does occur phase shift. Upper reflected occurs phase shift and upper transmitted occurs no phase shift. Remember that before entering into second beam splitter, the upper beam had phase shift of 1 pi. So the previous phase shift has been cancelled. Now the upper reflected occurs no phase shift and upper transmitted has phase shift of 1 pi. Next, let us follow the lower beam inside the second beam splitter. The second beam splitter splits the lower beam by 50% reflected and 50% transmitted. Remember that before entering into second beam splitter, the lower beam had phase shift of 1 pi. The light beam reflected by the front surface of dielectric beam splitter doesn't occur phase shift. Lower reflected beam occurs phase shift of pi and lower transmitted beam occurs phase shift of pi. So this is the situation at the end. If you see at the detector B side, the two beams are having different phases and generate destructive interference. And if you see at the detector A side, the two beams are having same phases and generate constructive interference. This is the reason the combined beam is expected to strike only the detector A. But this is what we are seeing in our test. The beams are reaching both detectors. The reason for this unexpected behavior is that the length of both upper and lower paths must be same to keep same phase in all time and location. But it is very difficult to us to keep same length at a nanometer level. So we are not able to see the beam strikes only detector A.
So some real-world applications of superposition. In quantum computing, it's used for photonic qubits in superposition and quantum gates using beam splitters. In quantum cryptography, it's used for secure key distribution and eavesdropping detection. And for quantum sensing, it's used for gravitational wave detectors and ultra-precise measurements. So thank you guys so much for watching this lecture video, and make sure to check out our next one on measurement and Stern-Gerlach.